Thanks, Hugh, for putting this together and for inviting me to be a part of this symposium. It's a lot of fun to be here and to be able to tell you about some of our chemistry. And I thought I would start with an overview of our group and our interests, and then tell you a few stories where we've been able to use CH functionalization and total synthesis. And I'll say that you know, our group is interested in the synthesis of complex, stereochemically rich polycyclic natural products, and I show a few of those targets that interest us on the slide, and we're interested in these molecules from the perspective of thinking about strategy. How do we actually put them together? How do we design synthetic plans? And also because they provide us with a really nice opportunity. So if you go to the next slide, for thinking about reaction development and catalysis. And at this stage, we're primarily consumers of CH functionalization methods. I'll say that we haven't had a real programmatic effort in our own lab towards developing new CH functionalization methods, but we certainly think about how to apply them in the context of total synthesis. And I think over the course of the years, what we found are certainly opportunities for ongoing reaction development. And so as much as we continue to look at new methods, we often find ourselves employing older methods, and you'll see that in this talk today. So if we move on to the next slide. After getting the invitation to be a part of this symposium, I was thinking about chemistry where we have used CH functionalization in total synthesis, and it made me think of actually one of the first molecules we worked on in my lab at Caltech. So this molecule, Salvileucalin B, an unusual diterpenoid type natural product with this norcaridine that's sort of at the core of the skeleton. And it was really our interest in thinking about how to gain access to that structure that led us to pursue Salvileucalin B. And so this is an older synthesis, but I thought I would just show a few slides that that I think depict how we thought about or ended up using CH functionalization as a strategic tactic. So if you move on to the next slide, I show here our retrosynthetic analysis. And to be perfectly honest, this was not the original retrosynthetic analysis. It was something that evolved over time, but it gives you a sense about how we thought of the molecule. Ultimately, we decided that we're going to incorporate what we call the northern lactone of Salvileucalin B through a late-stage CH oxidation, and I'll come back to that. And that takes us back to this molecule that's in the center here, this enol triplet. And we thought we might gain access to that type of structure through an intramolecular arene cyclopropionation reaction of the corresponding alpha-diazo beta-ketonitrile. And that structure, in turn, could arise from a cyclotrimerization reaction of the corresponding triene. And so I show this slide because really we spent a little bit of time thinking about how to implement this strategy. And if you go to the next slide, what we found early on was that really we had to think about using late-stage CH oxidation to enable the strategy that we wanted to employ. So for example, if we tried to perform the cycloisomerization reactions on compounds that had the ester group brought in early. So instead of the triinyl ether that I show you, a triinyl ester, where we have oxidation, where we're going to need it at the end, that cycloisomerization does not work well. You're probably sitting in the wrong conformation in that ester. And so by going to the ether, that allows us to implement this cycloisomerization reaction. Moreover, we found that having electron-deficient arenes were bad for these arene cyclopropionation reactions, right? So the electronics, by being able to leave out that oxidation state, the electronics for the arene cyclopropionation are much improved. And ultimately that meant that, and we also thought there were some additional advantages, but ultimately it meant we were going to have to perform this late stage CH oxidation, which made us a little bit nervous, because if you look at that substrate, we have this electron-rich furan and other problems that could arise in terms of the chemistry. So I thought if you go to the next slide, I'll show you what we ended up doing. So that we use a ruthenium catalyst that allows us to engage this triene in a quite efficient cycloisomerization reaction that gives the tricyclic arene here. And we can elaborate in a few steps to the the alpha diazobeta ketonitrile. And for the key cyclopropionation, we use a copper hexafluoroacetic catalyst, which works pretty well. And I'll just point out that we're forming here a fully substituted cyclopropane, which was something that there really was very essentially no precedent for. And that in order to achieve that cyclopropionation, it was important that we had this beta ketonitrile as our sort of diazo group. So we were able to solve these problems, but that left us for the end to think about the CH oxidation. So if you go to the next slide, the chemistry that we ended up using, and you know, it's not perfect, is this chromium trioxide in the presence of 3,5-dimethylpyrazole, some conditions that were developed by a group at Upjohn. That allows us to gain access to some of the Salvileucalin B. And the reason that you can see that there are certainly shortcomings here, we also form this ketoaldehyde or undesired product. In fact, that's what's desired, that's what's favored under these conditions. And we tried a lot of other CH oxidation conditions that either gave unproductive oxidation of the furan, or we were seeing worse selectivities favoring the ketoaldehyde. And so although this certainly provides access to the natural product, and I think ultimately if we needed more compound, we could actually proceed by optimizing for the ketoaldehyde and converting that to the lactone. This is a challenge. And so in some ways my talk will be motivation to the center to continue to develop new methods, because it'd be very nice to be able to have a system that is guided perhaps by sterics instead of the more activated CH bond, to allow us to improve that chemoselectivity. All right, so if we move on, the next story I thought I would tell you about is a more recent effort from our lab, where we were interested in the synthesis of Ryanadol, and actually more recently related the natural product Ryanadine. And so I'm not going to take you through the whole story here. Once again, I thought I would just focus on the sort of key element of the synthesis that relies on CH functionalization. So if you go to the next slide, I'll give a brief overview of the retrosynthetic analysis. So the idea was that we could take Ryanadol back to Anhydroryanodol. We're going to build on some chemistry that was developed by de Longchamp in his first synthesis of Ryanadol. And so that simplifies the target really initially to this compound Anhydroryanodol. And so we were thinking about how to access this, this structure. We became interested in gaining access to the right-hand side of the molecule using pos and con chemistry. So that would provide access to the cyclopentenone that's in the bottom right structure there. And we liked this particular disconnection because we thought we could gain access to that structure through an intramolecular pos and con of the corresponding E9. As we were thinking about this route, one thing that was appealing was that we thought that the cyclopentenone had all of the functionality we needed for incorporating the oxidation pattern of Ryanadol in terms of that 5-membered ring. So if you go to the next slide, we envisioned that you could perhaps use allylic oxidation to oxidize that tertiary methine there. You can use enolate chemistry to oxidize alpha to the carbonyl to gain access to a diketone, and perhaps we could do some conjugate addition chemistry to install that final oxidation state at the bridgehead position or the ring fusion position. So this was the basic plan that we established, that sort of once again evolved over time for the synthesis. If you go on to the next slide, what we ended up finding was that we could indeed prepare this E9, and that this was a very good substrate for a rhodium catalyzed pos and con reaction. We can use only 1 mole% catalyst, and so at that type of catalyst loading, it actually becomes cost competitive with some of the stoichiometric metals that are often used. The products form in good yield as a single diastereomer. We've done this on reasonable scale. So at this stage, we were really left to contemplate how we were going to actually reduce this idea of using late-stage oxidation to practice in terms of the cyclopentenone oxidation. We initially looked at conditions that we thought would allow us to oxidize that CH bond that I have highlighted using either directed methodologies or radical reactions without a lot of success. And so it was at this stage that we started investigating whether or not we could oxidize alpha to the ketone to get up to the diketone. We had some model studies that showed that we could do that chemistry on related systems. So if you go to the next slide, what we found is that we can use selenium dioxide, acetic acid, and dioxane at 100 degrees. And we were able to form this product on the right in about 60% yield. So what we've achieved here is we've oxidized up to the diketone, and then we actually see what looks to be the product of a formal hydration reaction, where you're getting hydration of the ene diketone to give the product. Now, I say appears to be hydration because what we know is that we have never isolated a product in this series where we've oxidized up to the diketone and we don't see that the incorporation of that ring fusion alcohol, that hydration product. And that's led us to wonder if it's not actually a hydration, if water, especially because we've run these reactions sort of under conditions where we didn't think that we would see hydration. And that's led us to wonder if perhaps the mechanism is somewhat different. So if you go to the next slide, maybe what's happening is that under these conditions, we're getting enol, dienol formation, and you're going through more of a 4+2 type mechanism. And that's why we would always see sort of these oxidation states incorporated in tandem. So at this stage, we were excited about this result. It certainly led us to focus now on incorporation of that last oxidation state. And then to do so, we really wanted to think about whether or not we could improve the yield of this reaction. So we started looking at various conditions using selenium dioxide, but perhaps buffering. We thought that one problem might be that the bond groups are falling off at 100 degrees in acetic acid. And so we started looking at conditions where we didn't have acetic acid present. And if you go to the next slide, ultimately what we found is that if we use, actually sometimes you can use potassium phosphate dibasic or leave that out and just use boranes from molecular sieve, so strictly anhydrous conditions. Under otherwise identical reaction conditions, we see not only the oxidation up to the diketone, the incorporation of the formal hydration product, but also this final CH oxidation, which provides now the ring fusion diol exactly as we need for elaboration to the natural product. So there's still a lot we don't understand about this reaction. If you go to the next slide, we have looked to see whether or not the partially oxidized product is en route to the fully oxidized product. And what we see is that if you resubject that compound to the reaction conditions, we don't see further oxidation. And this leads us to question whether or not this intermediate that we propose for the oxidation to the hydroxyketone actually is en route to the final oxidation, that you have to intercept this intermediate prior to hydrolysis in order to gain access to the final oxidized product. The one other thing I'll point out here is that we didn't actually design this reaction. This was not a reaction that we envisioned from the very outset, but I think the reason that we encountered and discovered this reaction was because we were targeting these types of late-stage CH oxidations. And it was by going after the cyclopentanone that we put ourselves in the position to reveal some pretty interesting chemistry here. If you move to the next slide, I'll just show that this intermediate is a key intermediate in the synthesis of both Ryanadol, so we can elaborate from there in just 6 steps to Ryanadol, or if we change the steps a little bit, we can elaborate in an additional 9 steps, so 18 total steps to the natural product Ryanadine, and that's some work that we just recently published within the last couple of weeks in ACS Central Science. So the third story I thought I would tell you about, if you move to the next slide, is some work on a natural product, Psiguadial B. This is an interesting compound. It has sort of a union of a terpenoid part of the molecule with a fluoroglucinol fragment. And we were interested when we started targeting this structure really in thinking about how do we gain access to this unusual 6-7 bridging system that then is transfused to the cyclobutane. And so in this in considering our approach to these molecules, we really thought a lot about incorporating methods for CH functionalization. If you go to the next slide, one of the early retrosynthetic analyses that we drew up is shown here. We thought maybe we could simplify Psiguadial B back, where we would incorporate those two aldehydes via late-stage formylation chemistry, and that perhaps we could form the bond that's highlighted in purple for that central structure from the corresponding benzophenone derivative using a Norrish type 2 type functionalization, where we would basically, through this disconnection, you reveal sort of embedded within the molecule a potential benzophenone type intermediate that you could imagine upon irradiation could give rise to the excited triplet state that could undergo hydrogen atom abstraction and then radical recombination to form that carbon-carbon bond. And certainly this is a tricky transformation to reduce to practice. So you can imagine at least 3 different methylenes from which you have potential hydrogen atom abstraction that could occur. And so certainly a risky disconnection, but something that we thought was worth pursuing. If you go to the next slide, that allows us to then perform the following retrosynthetic analysis, where we're going to incorporate that arine through a palladium catalyzed CO bond formation. And that takes us back now to this structure that's in the middle on the bottom row, this cyclobutane fused to a cyclohexanone. In thinking about the structure, we really felt that the bond that I've highlighted in purple was a strategic bond. If you think about it in terms of how it's embedded within the natural product itself, it's connecting a 4-membered ring to a 6-membered ring, and it does so through these 2 vicinal stereogenic centers. And so we felt like if we could come up with a solution performing that particular bond, that would really enable the rest of the synthesis to come together. And so the method we were interested in was whether or not we could use a palladium catalyzed CH functionalization to couple this cyclobutyl quinolinamide with this type of cyclohexenyl iodide. So in the forward sense, if you go to the next slide, we start with this 2,2-dimethylcyclopentanone. We can convert that to the alpha diazoketone. And initially, in our early studies, we were just performing a Wolff rearrangement. So photolysis of the diazoketone in the presence of water gives rise to the corresponding carboxylic acid. And at that stage, we can couple the carboxylic acid with the 8-aminoquinoline to give the amide. And really, we're basing this approach on some really beautiful group chemistry by a couple of groups. So in the context of synthesis, some nice examples from Bill Barron's group, but obviously inspired by the work of Doug Gulis and Chen and Jin-Kuan Yu and many others in terms of thinking about how to use these types of CH functionalization reactions. And this chemistry translated quite well on this system. So we were able to sort of build these conditions off from some reports in the literature. Using palladium acetates, silver carbonate, we can form the desired carbon-carbon bond to give the cyclobutane with the cis stereochemistry in reasonable yield. And although we had originally thought that we should be able to insert into that cyclobutane CH bond, we weren't sure if those 2 methyl groups where you have accessible primary CH bonds would be problematic. And so we were happy to see that actually was not the case. So we originally formed the cis cyclobutane. We found that if you actually run this reaction and take the product and submit it to base, so if you go to the next slide, we actually see epimerization to give us the required trans stereochemistry across that cyclobutane. And that epimerization happens gamma to the ketone, so taking advantage of the acidity of this binylogous system, right, to do the epimerization. And so this was looking pretty nice, and if you go to the next slide, although I won't take you through it, we ultimately were able to install the quaternary center using conjugate addition chemistry, which is also nice because there's a lot of catalytic methods there that have been developed with using chiral ligands to allow you to control that stereochemistry. So I think this was a pretty nice solution. I'm going to detour a little bit from the CH functionalization chemistry and tell you about how this sequence of reactions actually led us to develop a new reaction to prepare these types of cyclobutanes in enantiomer-enriched form. So if you go to the next slide, we were working with these compounds, and I have to give a lot of credit to the graduate student working on this project, Lauren Chapman, thinking about the mechanism of the Wolff rearrangement. You get formation of the ketene, and her recognition that there have been a lot of reactions developed recently in which ketenes are engaged with a chiral nucleophilic catalyst to provide access to enantiomer-enriched products through these types of substitution reactions. So if you go to the next slide, one of the primary inspirations for our own work was that of our colleague Greg Fu, where he was using these planar chiral DMAP derivatives, and that allowed him to take stable isobal ketenes and react them with paroles to gain access to these types of amides here. And so the question was, can we photolytically generate a ketene in the presence of a chiral catalyst and our 8-aminoquinoline as a nucleophile and access the enantiomer-enriched amide? And if you go to the next slide, since it's a short talk, I won't take you through that reaction development, but we were indeed able to develop that chemistry. So if you photolyze the alpha diazoketone in the presence of 8-aminoquinoline, oh, sorry, go back, in the presence of synconine as a catalyst, we can isolate this product here in good yield and in reasonable enantioselectivity. We can actually recrystallize up to a single enantiomer without problem. We do this on gram scale. Now, I'll point out that I'm drawing the enantiomeric series that we were hoping to have so we could access the natural enantiomer of the natural product. And I'll come back to that in just a minute. But just to demonstrate the chemistry works, we can do this coupling and then the in situ epimerization, and it gives the structure that I've shown here. And it was really at this point that we were able to get X-ray quality crystals and assign the stereochemistry using single crystal X-ray diffraction. And unfortunately, we realized that synconine gives us the wrong enantiomer of the cyclobutane product here. So that was unfortunate. If you go to the next slide, really what we have is the stereochemistry as I've indicated now. So we're in the wrong enantiomeric series. We were able to correct that. Sorry. You can go ahead now. We were able to correct that instead of by changing which catalyst we use, which is one of the challenges and disadvantages of using cinchona alkaloid cinchona alkaloids as catalysts is that you can't just easily go to the enantiomeric series, and the pseudo-enantiomeric catalyst really didn't work well. So instead what we do is we take our amide, we perform the cross-coupling now with a different vinyl iodide, a vinyl iodide in which the ketone has been protected as a ketal. And that works again really nicely under the same conditions we developed previously. And now we can reductively cleave the auxiliary using Schwartz reagent and then expose to base, and that results in epimerization at the aldehyde center now. And so by changing which center we epimerize, we can access either enantiomeric series of this important building block. And so we can elaborate from there by a Wittig-olefenation, and that gives us a key building block. And we found that just by thinking about which order of events or changing the order of events in terms of when we epimerize, we can access either enantiomeric series of that intermediate. All right, so if we move forward from here, we did investigate this Norrish reaction to form the framework. It unfortunately was not viable in terms of yield. So although we do see what we've assigned to be some of the desired product, the yield is pretty low, and we see a lot of an unproductive CO bond cleavage event under these conditions. So if you go to the next slide, what we ended up doing was revising our retrosynthetic analysis. And here what we're going to do is actually incorporate the aldehydes once again at the end, but also this final carbon bond, this aryl bond, carbon aryl bond at the end of the synthesis. So that's going to mean a CH functionalization of that highlighted methylene at the end. We can then go back through CO bond formation in an intramolecular sense now, and we can form the terpenoid part of the molecule through ring closing metathesis. And then that takes us back to the same building blocks that we'd used previously. Excuse me. So if you go to the next slide, just to show you the chemistry we end up using, we can take that key building block I showed a couple of slides ago and elaborate it to this to the structure in the top left on the slide. We then perform a ring closing metathesis, and then can hydrogenate both of the double bonds in the system using Crabtree's catalyst to get very good levels of diastereoselectivity in forming the stereocenter alpha, or sort of that leads to the aryl bromide. And then following CO bond formation using copper catalyzed conditions, we perform this last CH oxidation chemistry. And so the approach that ends up working is that we can oxidize at that highlighted methylene using DDQ in the presence of ethoxyethanol. And then we take that ethoxyethanol adduct and we expose it to BF3. That basically activates ether, likely going through the carbocation type intermediate. Using this phenyl cuprate as a nucleophile, we can trap that out to form that last carbon-carbon bond. And although the yield is pretty good for that reaction, the diastereoselectivity is only about 2 to 1. And something that we were definitely thinking about as we were investigating this last sequence was that it would be really nice to be able to do a benzoic CH arylation. And we tried some chemistry there, but without a lot of success. So I'll once again put that out there as the type of transformation that would be enabling and further streamlining in these types of total synthesis contexts. If you go to the next slide. So finally, just an overview, sorry, of the synthesis. We can elaborate to this key intermediate that I've highlighted in the box. We can get either enantiomer from the same enantiomer of the cinchona alkaloid catalyst, so from synconine. So I think that's nice. We can then elaborate through the synthesis, and we really leverage a couple of important CH functionalization reactions within this total synthesis. So both in terms of forming the key carbon-carbon bond between the cyclobutane and the cyclohexanone fragment, but also at the end for incorporating that final phenyl substituent. And so if you go to the next slide. So certainly in our lab, when we think about accessing these molecules, we often rely on CH functionalization, either a CH oxidation reaction or CH functionalization that results in direct carbon-carbon bond formation as a strategic tactic in target-directed synthesis. And I think that what we also see is that the substrates that we subject to CH functionalization reactions are really challenging substrates. They're an important testing ground for the methods. They'll quite quickly reveal things such as incompatibilities in terms of functional group tolerance. And although we continue to use these types of reactions as tactics in our synthesis efforts, there's still a lot of work to be done. There's still certainly opportunities for improving the functional group tolerance, chemoselectivity, and improving things such as diastereoselectivity in these types of transformations. So I'll just close by going to the last slide and thanking my group. I have an awesome group of colleagues at Caltech that are a lot of fun to work with. Here's our most recent group picture. And in the bottom left part of the slide, you can see the people who worked on the projects I spoke about today. So early on, two of my first group members, Roger Nanny and Sergey Levin, worked on Salvileucalin B. The work on Ryanadol and Ryanadine was really a team effort by a couple of fantastic chemists. So Kangwei Chang and Chen Zhu really worked on the chemistry I talked about today. And in this most recent paper, Arthur Hahn has helped us not only access Ryanadine, but some other related natural products. And then finally in Psiguadial B, that was Lauren Chapman and Jordan Beck. So thank you.